back to EC 3030. And before today's technical discussions, here's an announcement on the homework 3, and it's due October 9th, next Friday. And you should be able to solve all the questions after today's lecture. And also on a note of the midterm grading, so we're still working on that. So we will go through the midterm solutions next week in the class. Alright, so then let's get started on the lecture 11th. So in the lecture 10th, we talk about the subthreshold region, but today we're going to go back for the saturation and the linear region of the transistor. So we're going to have further discussions on the IV characteristics. So this is like a part 2 of the MOSFET IV. So we're going to continue our discussions from the lecture 9 and 10. And we are going to switch the reference book to this Sedra and Smith. And you can find the relevant chapters here. And also we uploaded the PDF of those chapters to the Canvas. So the reason that we switch the textbook is that from now on, we are going to switch the topics from the semiconductor device physics more towards the circuit level design on the microelectronic circuits design. So for the rest of the semester. So we need to switch the reference as well. And this is a recorded lecture from the last spring. Alright, so then this is a review of the MOSFET device structure. And you have seen this in the lecture 9. And here is a quick recap. So we have the silicon substrate. For the N-type MOSFET, we have the P-type substrate, or sometimes we call it body. And then the source and drain will be heavily doped with N-type doping. And then we have the oxide to separate the gate and the substrate. So in this case, the oxide is a silicon dioxide. And we have two geometrical parameters. One is the W, that is the width of the channel. And the second one is the L, that is the length of the channel from the source to the drain. So those are the important parameters of the MOSFET structure, the W and the L. So the MOSFET actually is a 4-terminal devices. Normally we only talk about the gate, source, and drain, but actually it's a 4-terminal devices. So here to the bottom, for the substrate, it usually will have a contact, and this is called the body contact. So it has a symbol B here. Or in the circuit symbol here, you have seen this symbol before, and typically we will use the gate, drain, and source. But actually it has a body contact. So if we want to draw those 4 terminals, then we will add the body contact here. But in many cases, the body is not used in the real circuit because it's always ground in the NMOS case, or the body is tied together with the source to the ground. So the body is grounded, and very often the source is grounded, so it's like they are tied together. Normally we are going to apply the voltages to the gates and the drain. But in reality, it's a 4-terminal device, but we rarely use the body. Then let's review the MOSFET operations. We have discussed this in lecture 9. So this is cross-sectional view of the MOSFET, and we have the TOX, that is the thickness of the oxide here. And we have the L, that is distance between the source and the drain. So first we need to create this channel, because right now this is P-type channel. We need to invert the channel by applying large enough gate voltage. So let's say the gate voltage larger than the threshold. Then we create the channel, so this shaded gray area. That means we have the electrons in this case. But still, there's no current flow if the VDS, the drain and source voltage potential difference, is 0. So there's no current flow at this moment. But if we apply the drain current, a small drain current, VDS, is larger than 0, then the electrons will move from the source to the drain, and then current will flow from the drain to the source. And this is the triode or the linear region, as we discussed before. And then we can gradually increase the VD, the drain voltage. So if we increase the drain voltage, then this is what will happen in the channel. So the electron density in the channel will become non-uniform. So you have more electrons towards the source and less electrons towards the drain. The reason is that the electrons, when they move from the source to the drain, there's electric field horizontally or laterally accelerates the electrons. So electrons will move faster and faster. So for the drain side, the electrons moves faster. That means they are easier to be collected to the drain. So they have less number of electrons here because they move faster. So the shape of the channel will change like this. So we are going to derive the IV equation using these assumptions. This is the first order IV equation model. We have discussed that in the lecture 9. This is suitable for the long channel device. Long channel means the source and drain are far away from each other, for example, larger than a few hundred nanometer or to the micrometer scale. Then this is pretty accurate. So here are a few assumptions to derive the IV model. So first of all, we think the current is controlled by the electrons in the channel. And then second, the vertical field determines the electron density. So that means the vertical field, that means the gate voltage, will determine the electron density underneath the gate. Or to be accurate, if you think about the channel's potential here at the location, if we think this x direction and this is y direction, at the location y, we have the channel potential Vy. Then the charge at this particular location is determined by the gate capacitance Cox times the voltage difference between the gate and the channel. So this is a second assumption. And third assumption is that those charges are moving laterally due to the drift, and the drift will determine the velocity of those charge. And you know the drift currents will have this velocity proportional to the natural electric field, and the coefficient is the mobility. So how fast those charge moves. So this is the third assumption. So with those assumptions, then we can derive the first order IV equation. So here we're going to use a little bit different perspective to derive this. We have done the derivation actually in lecture 9, but today we are going to use a little bit different approach to achieve the same equations in the final conclusion. So let's do that. So here what we are going to do is to look at a particular location in the channel. For example, here as we discussed, if you think this is x direction, this is y direction. At a particular point y, we have this Qy, the charge density. And this charge density, as we just discussed, is proportional to the voltage difference between the gate voltage here and the channel's potential Vy here. The difference between the gate voltage and the Vy determines the charge density. But first, we need to use the gate voltage minus Vt to determine the voltage difference, because you need to invert the channel first. So we need to overcome the threshold voltage. So effectively, Vg minus Vt, that is additional voltage above the threshold, then minus the voltage at this particular location in the channel, that is Vy. So that is the voltage difference across this capacitor. Then multiply by the capacitance, then you get the charge at this location. So this Qy, you think this is like the one cross section of the channel at this point. So then the current, as we discussed a few times before, current determined by two factors. First is how many charges there, and second, how fast they move. So how many charges there? So the drain current at this particular point, you have the Qn, and also we need to consider the third dimension. So here we didn't draw it, but if you consider the channel has a width W, then the wider the channel, then the more charge under the gate. So you need to multiply by the W and the Q. So this ID is this QY W. And then how fast they move is the velocity of the charge. And the velocity, under the drift is the mobility times the electric field. And this E is the lateral electric field, let's say from the drain to the source. So this is when you apply the VDS, then the voltage across the channel will determine the lateral field. Okay, so then you plug in those Q into here and the velocity V into here. So eventually you get this equation. This is the drain current. And then we need to move on. So this is the same equation in the previous slide. So we need to represent the lateral field E using the voltage at that point respect to the location Y. So if this is X and this is Y, so at this particular point Y, you have the voltage Vy. So the electric field by definition is a derivative of the voltage respect to the lateral dimension. So that's why you have the dVy over dy. That is this electric field E. So you plug in that, and then we here move one step further. So we move the, after you replace that, you have dVy dy. So we move the dy to the left hand side. So from here to here, we move the dy to the left hand side, and then on the right hand side you only will have the dVy left. Okay, it's the same equation here. Then one more step, we need to do one integration. So integration from the source to the drain. So integration from the source to the drain. So the integration from the source to the drain on the left hand side means the distance y change from 0 to the L. Let's say from the source to the drain, it's from 0 to L. So you integrate from 0 to L on the left hand side. On the right hand side, it's about voltage. So from the source to the drain, voltage change from what? From 0 to VD. Because drain is applied VD. So then we can do this integration. So on the left hand side, because this is a constant, and you integrate a constant value over the distance L, you will get ID times L. And then on the right hand side, you still have those equations here. So now on the voltage side, so here we are integrating the VDS. So VGS is like a constant. So if you integrate the constant, then you will get VGS times the VDS. And then the second one, this is what you need to be careful, because this is Vy. So this is the variable. If this is the first order of this variable, and you integrate this by from the 0 to VDS, it's like you're integrating x. So the first order term, if you integrate, you get second order term, right? So if you do that, this one will give you half VDS squared. If you integrate this Vy from the 0 to VDS, you will get half VDS squared. Because this first order term becomes second order, and you have half in front of that. This is from your calculus. And then minus Vt still is a constant, and times Vd. Yes. So if you move the L to the right hand side, and also you extract the VDS outside, then what is left is here, this equation. You have seen this before. So this is the IV equation in the linear or the triode region. This is just a different way to derive this. Again, we don't require the derivation in this class, and what you need to know is how to use this one. This is important. So here are just some comments on this process of the derivation. You will notice that the charge Qy from the source to the drain in the channel will be non-uniform. As we discussed, there will be more electrons towards the source and less electrons towards the drain. The reason is that the current, if you recall, in this Qy at a particular point y is Qy, then the velocity is mu, and then E at this location y. So mu is a constant, is mobility. So the current is constant, mu is a constant. That means Qy, Ey, the product is a constant. The mobility and the current is continuous. Mobility is a constant. So then this is a constant. So here we see the product Q and E is a constant. As we move the electrons from the source to the drain, then the electric field will become larger and larger, and the charges will become less and less. So this is reasonable because the electrons get accelerated from the source to the drain, so they move faster and faster. But towards the drain side, we don't need so many electrons because they move fast. So the number of electrons towards the drain side will become less. But overall, the current is continuous. You have less electrons towards the drain, but they move faster. Overall, the current is continuous. Okay, I think this explanation actually answers your homework, one of the homework questions in homework 3. So you will basically summarize what I just said in the homework. All right, any questions here? Okay, so it's just like a recap of the lecture 9. So let's spend a few more words on the IV plot. This is a first order model, and we just plot the ID versus VD if we use the equations here. So you see is ID is a quadratic function of the VD, so it's a parabolic curve here. And if you draw that, it will be something like this. So first the ID increases with the VD, and it will reach the peak when the VD equals to the VG minus VT. But after that, it will drop if we follow that equation. Of course, this is not true. This one is not true, because at this point, we are going to reach the saturation region. So before that, this is this triode region. And after this, we are going to enter the saturation region. So then we cannot use this equation anymore. So this is invalid. So what will happen here is the channel will be pinched off when the drain voltage equals to, so at this moment, the VD is equals to VG minus VT. So we call this is the VD set. That is the turning point between the triode and the saturation. So at this point, because the charge towards the drain goes to 0, then we are not going to have more current, even you have larger drain voltage. So we are not going to have more current because the charge goes to 0. We are not going to provide more charges. Then the current will become saturation. This is true in the first order model, and later today we are going to correct this physical picture to describe the transistor's current no longer saturate, especially in the small channel device. So this is to the first order, and the pinch off will happen, and then the current will become saturated. So this is the IV. After we consider the saturation, then after you reach the peak, then it will become flat in the ID versus VD. And this is the turning point. And again, this is when the VD equals to VG minus VT. And this VGS minus VT is defined as a VD set. It's a turning point. And also you will see that we will give another name for this one. It's called VOV. And this is defined as the gate overdrive voltage. It's the same number but different definitions. So here we also call it gate overdrive VOV. Is VGS minus VT. So we show this ID-VD plot, and then you can also get the maximum current in the saturation. This is when the VD equals to VGS minus VT. So you just plug in the VDS equals to VGS minus VT. Then you can get this equation. So this is the current here, this level. So that is the saturation current if we assume the first order IV model. And this is called the square law because the drain current is squared to the gate voltage minus VT. You can also draw the IDVG curve. Right? There are two ways to draw the IV equation. One is IDVG, the other is IDVG. So if you draw IDVG, you will see something like this. And this is the threshold voltage, and we discussed in the lecture 10. So here is almost zero current, but it's non-zero actually. And then you will have this increasing of the current versus the gate voltage. And then still there is a turning point here. That is again when the VD equals to VG minus VT, and between those two, the transistor is in the saturation. and after that, this is like this linear region or the triode region. So here we have another approximation. We say that when the VD is very small, VD is very small. So you see here when the VD is very small, you can use a straight line to approximate this curve. So if it's a straight line between the ID and the VD, that means it's a linear function. So what circuit is linear between the voltage and current? So that is resistor, right? So that's why we call, in this case, the transistor is like a resistor, and then the resistance of this transistor's channel is given by this formula. How do we get that? So in this case, here, we are going to ignore the second order term in the triode equation. So that means we are going to ignore this one. When the VD is very small, we only consider the first order term, that is this one. We can ignore the second order term. So if we do that, then you see this ID is basically this one multiplied by the VD. So this one is like the conductance of the channel. You know, current is like conductance multiplied by the voltage, and then you can define the resistance is 1 over this term. This is this conductance, and then 1 over that, so it's this 1 over mu COX W over L, and then VGS minus VT, or you can use VOV, because here we define it as VOV. So that gives you the resistance of the channel. If the VD is very small, you can think that is like a resistor. So any questions here? This is more like a review of the lecture 9. Alright, so let's look at the transistor's operation regions. Depending on the voltage, so you have the VG and VD. So sometimes we say VG or VGS. So I use them equivalently. The reason is that in many cases, the source is grounded. So the VG is the same as VGS. But to be accurate, it should be VGS. Okay, you are looking at the difference between the gate and the source. That is the VGS. And also you are looking at the VDS here. But if the source is grounded, you know, it's the same as VG or VD. So I use those as equivalent. Okay, so here, depending on the gate voltage first. If the gate voltage is smaller than threshold, you know, this is so-called cutoff, or in more accurate way, we call it subthreshold region, and we discussed that in the lecture 10 on Tuesday. So here the current is almost 0, but actually it's non-zero if we consider this subthreshold current. And to be accurate, we discussed this is proportional to the exponential Q Vg minus Vt over this mkt. So this is like exponential small number because Vg minus Vt is negative. So this is like the exponential decay function into a very small value. It's very small, but it's non-zero. And we discussed why we want to consider this one, because this will contribute to your leakage power. Even when your processor is in the sleep mode, you are consuming the power because of this one. So today we are going to focus more on this saturation or the triode region. This is when the VGS is larger than the VT. And then now we need to decide saturation versus the triode by looking at here the VD. So if the VD is large, right, VD larger than this VGS minus VT, this is large, then the transistor is in the saturation. Or if it's small, then it's in this triode region. And in the triode region, as we just discussed in the previous slide, if we ignore the second order term, then the ID is proportional to the VD, so it's like a linear resistor, and the resistance is given by this formula here. So that's why in the triode region, when the drain voltage is very small, we can approximate the transistor as a resistor. But in the saturation, it's different. So we say that the transistor can be approximated as this VCCS. So what is that? This is the voltage-controlled current source. Voltage-controlled current source. Why is that? Because here in this equation, this current does not depend on the drain voltage. So here it doesn't depend on drain voltage. It's providing a constant current. But this current is controlled by the gate voltage. So to be specific, this is a gate voltage controlled device. It's gate voltage controlled current source. The gate voltage will determine how much current will flow through here. So it's like a voltage controlled current source. Any questions? Alright, so let's look at the parameters in the IV equations. So let's look at the square law for the saturation current, and we want to look into those parameters in more details. So this is the drain current equals to half mu. Mu is mobility. Mobility tells you how fast the carrier moves under the electric field. And we have the mu n for the electron mobility. And later, when we talk about the PMOS, we will have a mu p for the hole's mobility. So the mobility for electron is typically larger than that for hole. Electrons moves faster than the hole in the silicon. So this is the mobility, and mobility has a unit. This one, centimeter square divided by volts times the second. So this is the unit for the mobility. And then in the equation we have the COX. So what is the COX? That is the gate capacitance per unit area, and it's given by this equation. So epsilon oxide is the permittivity of the oxide. It's actually the epsilon 0. That is the vacuum permittivity times the relative permittivity or the dielectric constant of the oxide, and then divided by the thickness of the oxide. So this is the MOS cap. Right, you have the TOX thickness here, and then you have an area of this one. But we already normalized this to the. This is already normalized to the total gate capacitance divided by the area. This is normalized, so that's why the unit here is the Farad, is Faraday, divided by the centimeter square. Centimeter square is normalized to the area. So if you recall in this course, we prefer to use a centimeter for the unit of the length, and the centimeter square for the unit of the area, and the centimeter cube for the unit of the volume. So that's why you have this one. And then W over L, those are the width and the length, of the channel, and we have shown the schematic of the structure at the first page of this lecture. And if you recall the width and length of the structure, those are geometry of the structure. And then VGS minus VT squared. Okay. So here we have a few more definitions, a few more symbols. So here we can define the mu n CoX as a Kn prime. So this is when you look at the reference book, the Sedgwick Smith, sometimes they are going to use the Kn prime to represent the mu n CoX. One step further, if you further include the W over L, then you can use a Kn to represent this mu n CoX W over L. So basically all the coefficients in front of the voltage, you can use Kn. So the unit for the Kn prime is mu n times CoX. So basically you multiply by here the CoX and the mu n in the units. So the centimeter squared cancel. What is left is this Faraday divided by the volts and then the second. And it will be equivalent to this ampere per volt squared. So you know those units can be converted. There are not many fundamental units. In the SI unit system, there are only 7 fundamental units. So like the Faraday for the cap and the ampere for the current, they can be converted using like the volts for the voltage and second for the time. So those can be converted. And then Kn will have the same units, ampere per volt square. So then this is because W over L is unitless. Those two units will cancel. Okay, so this is the parameters. And then the next question is, can you change it? Can you change those parameters? Then this question depends on your role here. So those parameters can be divided into the design parameters and the technology parameters. So here design parameter means the circuit design. So that means if you are a circuit designer, for example, if you work for Apple, you work for NVIDIA, those are the design companies. They don't really fabricate the chip. You only design the circuit. So as a circuit designer, then what you can do to modify the transistor is to change the width. This is always true. You can change the width. If you want larger current, then of course you see here you want larger width. And then you can also modify the L in most of the time. So the L depends on what? Depends on the technology node you use. What is the process? For example, you are using like Intel's 32 nanometer, or the TSMC's 28 nanometer, or Samsung's 14 nanometer. So you change the L, then by changing the technology node, the process. But you have to use different foundries, different technology for that. And then the gate voltage is always what you can change. The VGS is the voltage you apply. You can change that as a circuit designer. Okay, so if you are a process engineer, for example, hired by TSMC, then you can change more parameters related to the technology. For example, the threshold voltage. And if you recall what determines the threshold voltage from the lecture 8, you will notice that one important parameter is Na, the doping density. If you want larger threshold voltage, then you need to use higher doping. This is from your lecture 8. And the TOX actually should be changeable if you are a process engineer. So you can change the capacitance here, the gate oxide thickness, and then you can change the COX accordingly. And then the mobility is the most difficult to change because this is silicon's property, how fast the electron or the hole move in the silicon. So it's very hard to change that. But nowadays, the engineers are trying to improve the mobility by inserting like germanium into the silicon. What is like a short channel transistor. So it's no longer like a pure silicon because germanium, the mobility for the germanium is higher than the silicon. So if you have some silicon germanium alloy instead of pure silicon for your substrate, then you are going to improve the mobility. But this is not very easy to do. So this needs a lot of effort in the fabrication. All right, any questions here?